Good afternoon, Prof. Teo. I'm Jie Yi, and today my team and I, consisting of Debdeep, Arshita, myself, Wei Long, and Win Soon, will be going through the use of CNN in the diagnosis of COVID-19 using chest X-rays. So this is our agenda for today, and we will start off by identifying the business problem. So COVID-19 is nothing new to us. In April of 2020, we saw the highest daily caseload of more than 1,000 new infections. So clearly, COVID-19 has put a strain on Singapore's public healthcare system. Firstly, we've had to construct purpose-built non-medical facilities as hospitals ran out of space. This is in reference to things such as the Singapore Expo. The second thing is that a group known as the Singapore Healthcare Corps was launched to recruit healthcare professionals to volunteer to plug this manpower shortage. These professionals were those who had retired, those who had left the sector, or even those from the private sector. Lastly, on the finance side, $4.8 billion was set aside just 2 months ago to safeguard public health. This is on top of more than $100 billion that have been spent on COVID-19 already. So COVID-19 is far from over, and Singapore should look at improving its systems and processes in preparation for its long road to recovery and future health crises. So how can Singapore's COVID-19 response be optimized? Well, the key is to accurately and timely detect COVID-19 patients in order to control its spread. And how can this process of COVID-19 testing be optimized? Well, there are currently three main ways in which this is being done. The first way is the PCR or swab test. It is the most accurate and most commonly used test. It's considered the gold standard of COVID-19 testing. So the second test is the antigen rapid test. It's far less accurate than the PCR, but it has a faster turnaround time, and it's typically used for pre-event testing. So the third and last test is the serology test. However, this test only detects past infection, even though it does have a faster turnaround time. It's now only used for travelers whose destinations require it. Apart from these three main ways, in our research, we found other ways in which COVID-19 can be diagnosed from alternative ways. So this alternative way is the chest X-ray. It has a faster turnaround time, is relatively cheap, is less invasive for patients, and most importantly, there's no contact with viral content. So where does technology come into play? Well, we've taken inspiration from a use case at NCID last year. So traditionally, suspected COVID-19 patients must undergo a chest X-ray when they are admitted to the NCID. After which, radiologists will scan for white patches in the X-ray images, which are then used to determine the severity of the respiratory infection. The final diagnosis is used to allocate hospital resources more efficiently to improve patient outcomes. So the technology that was used was an AI tool known as Radiologic, which helped to flag out images with abnormalities. This helped to expedite the process by 20%. From here, we can see that technology can be used to optimize the use of manpower, money, and medical resources. So as such, our team set out to see how AI can be further used in the optimization of the process of diagnosing COVID-19 using chest X-rays. So now I'll pass my time on to Deep.
We will be applying CNN models on chest X-ray images to automate the process of diagnosing a patient with COVID-19. Filters are applied on the input image, and the resulting values are batch normalized, passed through an activation function before pooling the important values. This is a convolution block. The output is then flattened and passed into a fully connected neural network, and its output is the class prediction. The input is a scaled 200 by 200 picture, and the filter applied is a 3 by 3 matrix. The dot product results in one value. As the filter moves across the rows and columns, the output is a 2D array. 96 such filters are applied, and the 3D tensor is then batch normalized. The ReLU activation function makes non-positive values 0, meaning insignificant, and the max pooling extracts the important values. Applying different filters is important in learning the key image features. The convolution can be done multiple times with differing filters, and the reduced dataset now contains the key features of the image. The values are put in a 1D array and passed as the input into the neural network. Batch normalization and ReLU are also applied here before passing data to subsequent layers. For the output layer, the sigmoid function is used to predict one of two classes. The data is passed in batches of 32 for better generalization, and 15 epochs are run till validation accuracy is optimized. The data comprises of chest X-ray images from patients divided into either positive or negative for COVID-19. There are 891 negative and 337 positive images available in total. As you can see, any untrained personnel cannot accurately diagnose solely based on the images, so utilizing AI technology to automate the process will reduce the dependency. The train set is what the model uses to learn. For each iteration, the validation set is used to check how the model performs on unseen data and update the weights accordingly. This reduces overfitting during training itself. Finally, the test set allows us to see the model's predictive performance on unseen data. The number of positive and negative samples for each train, validation, and the two test sets are shown here. All images were scaled to standardize the model inputs. As mentioned, the batch size of 32 and 15 epochs were used. The dropout rate of 0.3 is used to randomly omit some nodes from updating the weights to reduce overfitting. 2 and 3 convolution layers with 64, 96, or 128 as the starting number of filters, and also 1 and 2 dense hidden layers with 128 or 256 starting nodes were the tweaked parameters used. Hence, a total of 24 different models were trained and each model file was saved. The best two models were selected based on the optimized parameter found and which gave the validation accuracies and also minimized the validation loss. The first model had 2 convolution layers with 96 and 48 filters, respectively, and then one hidden dense layer with 128 nodes. This model had the lowest validation loss out of the 24 and the second highest accuracy. Adding just one more dense layer with 32 nodes gave the best model out of the 24 with highest validation accuracy. Additionally, this model has greater test accuracy and also much less overfitting issue as the test accuracy was much closer to the train accuracy. The second model had lower false positive and false negative values on the same test data. In this context, false negatives are of higher danger as it means failing to correctly identify a positive COVID-19 case and misclassifying it as safe. The second model also has the highest overall accuracy of over 90%, and it is important to note that the sensitivity value is lower than the specificity, meaning it is less accurate in correctly identifying a positive case compared to a negative case. Although the sensitivity of Model 2 is still higher than that of Model 1. Most importantly, when compared to the traditional doctor diagnosis of COVID-19 from chest x-rays, the models that we have far outperform the traditional methods and have significantly higher sensitivity, specificity, and overall accuracy values. To conclude, Model 2 is the best CNN model that we have derived and is suitable for further business implementations. Now I would like to pass my time over to Wei Long.
Thanks, Deep. Now I'll talk about the implementation and scaling of our solution. We exported the CNN model that we created and used a graphic user interface using the Tinker package to create an application that we call the COVID-19 diagnosis tool. This application gives a diagnosis for the user when they upload their X-ray images within 2 minutes of whether they are positive or negative for COVID-19. Let us begin with a demo to show this.
So this is the COVID-19 diagnostic tool written in Spider using the Tinker library. So you can see that we also created a function called predict COVID that actually calls the CNN model that we have created earlier and runs it against the X-ray image that will be uploaded by the user to give an output to the user of whether he or she is positive or negative for COVID-19. So without further ado, let us run our prototype. So in the landing page of our COVID-19 diagnostic tool, you can see that it serves two business users. Firstly, to the public as a self-help tool for them to get their diagnostic results without going to the hospitals. And secondly, for medical personnel to retrieve the results of the users, as well as for crowd control purposes to get only the most severe and urgent cases to come to the hospitals in the event of a major outbreak where resources are scarce. For example, a lack of hospital beds and oxygen ventilators for treatment. So we'll see how our COVID-19 diagnostic tool works for the public first. So to get a diagnosis, users must first select their preferred login details, and this will give them a personalized record later on for their results. So create account. So once the username and password is decided, users will proceed to create a medical record in our system. So for the example, for this, I will use Alex Ng, a fake persona. So we'll also ask Alex to indicate his medical conditions and how long they have actually persist. So this is to help medical personnel to gauge how severe his symptoms are and whether there's a need to rush him to the hospital immediately. In this case, whether he should be prioritized. So for our example, Alex has breathing difficulties for less than 2 weeks. Next, Alex will proceed to upload his X-ray photo. So when Alex press upload, a window will open to select his picture. So we have selected this picture randomly from the pool of X-ray images that we have. So once Alex selects it, there will be a window for Alex to confirm whether this is the image that he has actually selected. So once Alex confirms it, it will actually call the predict COVID function. As you can see, TensorFlow has started to run in the background to give a prediction to Alex. Next, Alex will be prompted to submit his information. So once Alex submits his information, his medical record details will be captured in our system, and he can proceed to log in to retrieve his results. So now Alex will be able to log in. And you can see in his personalized dashboard, it says for Alex Ng, his test results unfortunately is positive, and his visit to the hospital is currently not required. And this is because in the scenario where the hospital is very overwhelmed with COVID-19 cases, and they can only attend to the most urgent and severe cases. So when things are finally settled down and there's capacity for Alex to come in for treatment, the medical personnel will search by filtering conditions. For example, now breathing difficulties. Alex records will pop into the dashboard of the medical personnel, and the medical personnel can send a notice to Alex to come to the hospital for treatment. So status updated for Alex dashboard. So when Alex logs in, he actually says that his visit to the hospital is now required and he can come to the hospital for treatment. And he will be contacted by the hospital via his email address or his contact number that is existed in his medical record. So this facilitates the COVID-19 treatment and diagnostic process.
To tackle the business problem, our COVID-19 diagnosis tool can be deployed in 3 ways. Firstly, as a public self-help tool to allow users to easily upload their X-ray images and get their results within minutes. Secondly, mobile X-ray vehicles can also be sent to quarantine centers and the heartlands for the elderly who are less tech-savvy to get tested. This is important as they are a vulnerable group, and this will prevent them from going to hospitals and increase the chances of them interacting with potentially infectious patients. And lastly, lab technicians can also be trained to use our tool, giving doctors more confidence in their diagnosis as a second opinion to prevent the consequences of a false diagnosis. For business implementation, the COVID-19 diagnosis tool can be hosted using cloud service providers. And this gives 3 benefits as well. Firstly, cost effectiveness. An on-premise setup requires higher costs as it will require in-house server hardware, software licenses, and also to train IT employees to support and manage any issues that may arise. For the second benefit will be the ease of scalability. Most cloud solutions providers offers their services as a subscription service, and this can be easily scaled to increase capacity based on the demand of the hospital. So backed by the massive infrastructure by these service providers, the hospital can have access to additional computing power and storage whenever they need them. In the case when COVID-19 dies down and there are no more cases, the hospital can easily cancel their subscription as well. For the third benefit will be the reliability and security of cloud applications. So gone are the days where cloud has been perceived as less secure. Using an example of a leading cloud service provider, Amazon Web Services, they have numerous certificates on their security and is actively monitoring their system for any possible vulnerabilities in their system. So to keep our model relevant, we will be using data sets maintained by various radiology institutions, both local and foreign, for their COVID-19 X-ray images. So our model can be trained on a monthly basis using the images from these sources and will be able to adapt the various strains as it may arise. So going forward, we also use various CNN models such as AlexNet, GoogleNet, VGGNet to test our database to see which gives us the best accuracy. So let me pass on my time now to Win Soon to talk about our business implications.
So now, I'll be sharing some business implications of using CNN on chest X-ray images to detect the presence of COVID-19. In comparison to the swab test, CXR imaging have a lower processing time and it is cheaper by at least 50%. Furthermore, the swab test is prone to cross-contamination during the extraction of the genetic material, transportation of the sample, or the analysis of the sample in the laboratory. This may introduce errors in the swab test result, which carries financial consequences. Next, offering CXR as an alternative mode of testing may encourage more people to get tested. It has been observed that people in Singapore are avoiding the doctor because of the fear of swab tests. Deployment is less complex with the use of CXR and do not require one to come into close contact with many other potentially infectious persons. Wei Long has mentioned about the scalability of using CNN in chest X-ray images or CXR. This can reduce the strain on frontline workers. A mass deployment can be used as a mitigation plan in the event that there are subsequent waves in the future, in which we can deploy a lot more mobile X-ray vehicles quickly to afflicted areas such as high-cluster communities, houses, or dormitories. Deep has also shared with us that using CNN on chest X-ray images produce a decently high accuracy, which is higher than CT scan and doctor's judgment on chest X-ray. This will help to reduce cases of false positive and false negatives. There are severe consequences if these errors goes unmitigated. So looking at false negative, misdetection will increase the risk of infection within the community and thus propagating the pandemic. And this will also disrupt business operation, which affects the whole economy negatively. Looking at false positive, wrong detection causes unnecessary quarantine, result in a loss of income and increased costs for individuals. This can also cause disruption in businesses as well, as seen from the recent case where in December 2020, a cruise to nowhere had to return early due to a false positive detection. Therefore, having an increased accuracy helps to reduce this error and reduce unnecessary losses during this period. So next, Arshita will be sharing some limitations faced.
I'll be talking about the limitations of the model. The rapid spread of COVID-19 and the serious effects it causes in humans makes an early diagnosis of the disease imperative. The early identification of the disease, as well as the evaluation of its evolution, is a primary task for the timely application of medical protocol. Although CNN can help identify the virus, the model is not without limitations. Firstly, we have the inadequacy of data. Despite the increasingly large number of COVID-19 cases, there are not enough images that can be used to continuously train the algorithm. Since it is the legal right of the patient to decide when, how, and to what extent the hospital can access their medical information, the hospitals generally protect the patient's confidential information to avoid legal problems. This is one of the primary reasons resulting in a small data set. Secondly, we have the limitation of class imbalance. If the class distribution in the model is skewed, the formulated algorithm might be biased. It is much easier to get the CT scan results of individuals before COVID-19 as compared to after COVID-19. As a result, instead of recognizing the symptoms for the virus, it might start looking for signs that the individual does not have the virus. Thirdly, we have the regional differences. Individuals in different regions react to the virus differently. This is due to the various mutations of the virus present at different locations. For instance, B117 mutation of COVID-19 is more transmissible with more severe symptoms and is commonly found in the United Kingdom. Since data in regards to the COVID-19 patients is not easily available, the researchers have to use data from multiple regions, making it biased. Lastly, we have the limitations due to inaccuracies and false positives. A challenging task while using CT scan is to differentiate between COVID-19 amongst the various types of ailments. In fact, both early lung cancer and COVID-19 produce similar findings in the CT scan. Without the presence of a sufficient data, the algorithm might be unable to differentiate between the various diseases. Hence, an individual with other ailments can be wrongly diagnosed as COVID-19 positive. However, with the constantly improving technology, there is no doubt that the models can be adjusted to overcome these hurdles and further be used in other spheres of healthcare industry in the future. Since CNN medical image classification detects the anomalies with higher precision than human eye, CNN can be used extensively in healthcare. Timely diagnosis is the foundation of every efficient healthcare system. Especially when the patients are in critical condition, every second becomes crucial. According to research, using CNN can help the doctors to identify the disease 12 to 24 hours earlier by comparing the individual symptoms with other patients. For instance, CNN can be used to diagnose and detect the presence of other viral infections causing pneumonia. Given that pneumonia was the second leading cause of death in 2019, resulting in more than 20% of the total deaths, the use of CNN in Singapore can be extremely beneficial. This will aid in assessing the disease at an earlier stage, enabling the patient to get the required treatment early on. This will potentially reduce the mortality rate as well as the overall healthcare costs. CNN can be further used to provide a pre-diagnosis for the patient to detect ailments and prescribe medication. The AI system can use the patient's data to come up with clinical suggestions after analyzing and reviewing the patient's symptoms as well as its medical history before the patient visits the physician. This will streamline the process, save time and cost for the physician. To conclude, CNN can be potentially used for cutting-edge research institutions to find solutions for complex health problems. With an extremely high number of promising use cases, strong investment from major players in the industry, and a growing amount of data to support cutting-edge analytics, deep learning will no doubt play a central role in the quest to deliver the highest possible quality care to consumers for decades to come. Thank you.